Good evening, everyone. My name is Aditya Sharma, and this is a Power Plant System Engineering course being conducted by Department of Mechanical Engineering, IIT Guwahati, under the NPTEL program. And this is a live tutorial session for this course only. And we are into the eighth week of this course. This is a 12-week course, all right, and related to your eighth week week's content, we will have a discussion today, and we will see a few questions also. So, in last couple of sessions, we have been discussing different parts of vapor power system. Okay, so we will continue with that series in this session also. The instructor for the course is Professor Niranjan Sahu, and he is from Department of Mechanical Engineering, IIT Guwahati only, and I am a research scholar here. I also belong to, sorry, Department of Mechanical Engineering. So we shall wait for another couple of minutes. After that, I shall start today's session. Thank you. Okay, so I believe we can start with today's session. So in total, today we have three lectures to discuss and questions related to those three lectures. First lecture is on your condensers, steam condensers. Then next second lecture in this week's content is on your feed water heaters, right? So first is your condenser, then is your feed water heaters, then third is your cooling towers. So these three topics we are going to discuss and questions related to these three topics. So first we will discuss one lecture and then questions related to that, and then next lecture and questions related to that, and so on. So this way we will conduct our session. So we have been doing this previously also. So let's move ahead with this session. So first lecture is on steam condensers. So basically, if you see your TS diagram, okay, so something like this. So this part is your condenser, right? I hope you all remember, and this is your for your boiler, right? Something like this. So here you have your condenser activity going on, okay, and this is your expansion. In this direction is your expansion from your turbine, expansion of steam, right? So now the topic is condensate feed over water system. So two terms are there. Condensate is the steam that we are condensing, and the feed water is the water that we are feeding to our boilers. Okay, so these two things are there. Then why we are discussing, so condensate is fine. Why we are discussing feed water? We are discussing feed water because what we do is we don't plainly give the feed water to the boiler, right? What we do is we increase its enthalpy by somehow heating it, okay? And that is done with the help of a feed water heater. So that is why this combination has been used here, okay? Then, yes. So then coming on to your condensers. So condensers are of two types. One is your direct contact condenser. Second is your surface condenser. So what happens in a direct contact condenser? So if we are condensing steam, right? So the cooling element comes directly in contact with your steam, right? So for example, if we are using water to condense your steam, right? So the water will directly come in contact with the steam. So this is your direct contact. Then is your surface condenser, where your cooling element, right? Or we can say your cooling water doesn't come in directly contact with your steam that we want to condense, right? So most of the times it is a combination of your shell and tube combination, okay, for your surface condensers. So these are your two types of condensers. All right. Then there are types of direct contact condensers, right? So one is your spray condenser, then is your barometric condenser, then is your jet condenser, right? And in your surface condensers, there is de-aeration concept, right? Then heat transfer analysis has been discussed, and the design aspects of a surface condenser. Okay, so these topics have been discussed in your lecture number 18. So if you talk about your spray condenser, so what is peculiar about spray condenser? So your cooling water is sprayed into steam. Okay. Cooling water is sprayed into steam. Okay. So this is your spray condenser, right? Then is your barometric. Please remember these are all direct type of condensers. So what is your barometric condenser? So in your barometric condenser, so it is something like this. So this is your hot well. So from here we get our steam, right? And this is your static head. Here you have your static head. So this is your basically tailpipe, right? So what happens here is your vacuum in the condenser, okay, is achieved by virtue of static head from your tailpipe. Okay, so this is your barometric condensers, right? And at your hot well you get all your condensate, and from here you need to remove all the non-condensable gases. Okay, so this is your barometric condenser, right? Then next is your jet type condenser. So what happens in your jet type condenser? So your tailpipe is replaced by a diffuser. Okay. So what is its use? How is it different from your barometric condenser? So it helps to raise the pressure in a shorter distance than the tailpipe. In your barometric condenser, if you need to increase the pressure, then you'll have to increase its height, right? And that means its length of the tailpipe. But in your jet type condenser, you achieve this by shorter distance only. Okay. So the design is in such a way that you achieve in shorter distance. So this is your jet type condenser, right? Then is your surface condenser. So it is a shell and tube type condenser. So in shell we will have the steam, and in your tube we have circulating water or cooling water. Okay. So I'll just draw a rough diagram of one surface condenser. So this is basically a shell. Then you have tubes. And in these tubes, your cooling water will move. That will help to condense your steam. So this is your water box. Here is your another water box. Okay. So this is your undivided water box. Okay. And this is your divided water box. So these are supports for your tubes. Okay. From here, your steam exhaust turbine exhaust, okay, in the form of steam. So this is your turbine exhaust that is entering from here. At the bottom, you have collection of your condensate. Okay, so your condensate will be collected here. I hope you all are clear with what condensate is. Okay, the steam that condenses, that is coming from your turbine exhaust. Okay, so this is your condensate. This is your hot well where all your condensate collects. So what happens is your turbine exhaust comes from top, and then your cooling water enters the tubes. So this is a tube. Okay, so cooling water enters the tubes, right? It reaches undivided water box, then again it, for the second time, it moves from the one half of the tubes that is left, right? And then it moves to the outlet, right? So this is a two pass type of surface condenser. So there are cases where water moves only once, right? That is one pass, single pass. Then if the water is moving, the cooling water is moving two times, that is two pass, right? So this way. All right. So this is your surface condensers. Then what is de-aeration? So de-aeration basically is moving your non-condensable gases. So why do we need to remove non-condensable gases or non-condensables for that matter? Because they have negative effect on the performance of your whole system. Okay. So for example, if your non-condensable, you have non-condensable gases, right, in your condensers, so they will blanket your surface, right, tube surface, and this will eventually reduce the heat transfer. Okay, so that is why we need to remove the non-condensables, right, from your condenser. Then is your heat transfer analysis. So in heat transfer analysis, one parameter so this is your T saturation, okay, of your steam, right? And this is your, so this belongs to your steam, this belongs to your cooling water, okay? So initially it has some temperature, then eventually its temperature increases, right? In this state, in its final state, and this is delta T naught, okay? And this delta T naught is also known as your TTD, What is TTD? TT is D is your terminal temperature difference. Okay. So this is terminal temperature difference. Okay. So we have questions on terminal temperature difference. So there we will see it. Okay. So I have introduced you to terminal temperature difference. Now design calculations. So in design calculations for your condenser, we see the heat loads, right? So what heat load we are targeting and calculations related to that. Okay. So this all has been discussed in your design calculations or considerations. Okay. Then moving on to questions. The first question says that your barometric condenser is a surface condenser. So this is not a surface condenser. Okay, that we clearly know, right? So it's a direct contact type of condenser. Okay, so this is a false statement. This is a direct contact type condenser. Okay, so this is a false statement. So we have spray type, okay, barometric type, then we have jet type. So these are three direct contact type condensers. Okay. Then next question. So in a spray condenser, a part of condensate is sent to the feed water system while the remaining is sent to the cooling tower. So whether this is true or false. So what happens in your spray condenser? So it is like this. Here you have cooling tower. Okay. Then from here you have this chamber. Okay. From here this moves like this. Okay. From here you get turbine exhaust, or which you call as steam, right? From here you get cooling water. Okay. Somewhere here you will have your cooling tower. Okay. Then here what will you get is your condensate, right? So some part of your condensate goes to your cooling tower in your spray type condenser. Okay. while other is sent to your feed water system, where it is sprayed like this. Okay. So in a spray condenser, a part of condensate is sent to feed water system while the remaining is sent to your cooling tower. So this is a correct statement. Okay. So this was about your question number two. I hope this is clear. Spray condenser, a type of direct contact type, right? Your water is sprayed here and your steam is coming from here, and they directly come in contact and condense the steam. All right. Then moving on to next question. This is on your surface type condenser. Okay. So please have a look at the question and try to think about the answer to this question. So this question demands that we draw a comparison between a single pass condenser and a two pass condenser. So I have earlier briefly discussed what a single pass condenser is and a two pass condenser is. Okay. So I'll just draw here. So I have here, so I'm shading it just to know that we have these tubes. Okay. So let's say these are tubes, right? Then we have one more. This is your single pass. This is your two pass. And from somewhere from here, you are getting your steam. Okay, that is to be condensed. So what happens in single pass is that if you have your cooling water moving through these tubes, so it will pass only once. Okay, so there will be no second time of this same cooling water passing through any other tube. Okay, so some cooling water has passed from your tube, let's say one, this is two, this is, so if your cooling water has passed from tube one, so it will not pass from any other tube, right? So same is for 2, 3 and 4. Okay, same is for your 2, 3 and 4 tubes. So if some cooling water is passing through one tube, it will not pass through any other tube, right? So, but in your two pass, what happens is first your cooling water will pass through one and two tubes. Okay. Then here it will collect, right? And then again it will pass through this water that was passing through one and two. It will again pass through three and four. So first it was moving in this direction, right? From right to left direction, it was moving in tube 1 and 2. Now when it has reached this water box, undivided water box, so it will now move from 3 to 4, but the direction this time will be from left to right. Okay, and here then we will collect, so this will be outlet, so this will be inlet, this will be outlet. Okay, this is two pass. Here it will be single inlet, and one time it will have, it will enter, and then it will pass. Okay. Then if you see the question, so now if you compare the single pass and two pass condenser, so in comparison to two pass your condenser, what will be the amount of water flow? Whether it will be one time or two times, three times or four times. So looking at these two figures, you can easily figure out that it will be two times, right? For single pass condenser, it will be two times. It will double. Okay. So this was your question number 3. B is the correct option. Now we will move on to next question. So two statements have been given to you. Based on these two statements, you have to answer that which of the given options is a correct option. So please have a look. So which of the following options is correct for non-condensable gases in a surface condenser? So we have a surface condenser, and about non-condensable gases, two statements have been given. So these non-condensable gases result in severe decrease in condensing heat transfer coefficient of the surface. And why this happens? Okay. So next statement is they blanket the heat transfer surfaces. Okay. So heat transfer surfaces basically is the surface of the tubes in a shell and tube type of arrangement. So they blanket the heat transfer surfaces. So looking at the two statements and then looking at the options given. So first says that both the statements are true and one is the explanation for second. Second, B option says that both are true and two is the explanation for one. Third says that one is not the correct explanation for second. So, or and fourth is says that both one and three are false. One and two are false. So, if you see the both the statements, so you will realize that both the statements are first of all correct. Then second is that your second statement is the correct explanation for your first statement. So that is the uh, reason why what is written in first statement stands true. Okay. So in that case, your second option is correct. Okay. But also, if you see your C option, that also comes out to be correct. Okay. Because if you say one is not the correct explanation for two, that is also a correct statement. But maybe I should have avoided this option. Okay. Otherwise, both B and C becomes correct options, right? Anyways, I hope you have got the point about this question, right? So this was your question number 4 on your non-condensable gases in your surface condenser. Then moving on to your next question number 5. So this is about a condenser again and asks about terminal temperature difference. So we have seen what terminal temperature difference is. So what it does to your temperature, water temperature rise. So please think about it. So that if the terminal temperature difference is higher, what it basically does to your water temperature rise. This is a question number 5. So this is your cooling water, right? So if your TTD, terminal temperature difference, increases, this means, so if let's say this is point A, this point B. So this point B will come down, let's say to here. Okay. So there will be what? Increase or decrease in water temperature rise. So there will be a decrease in water temperature rise. I hope this is clear. So this was on your terminal temperature difference, a question on terminal temperature difference. All right. So let's see next question. So we have two questions. Sorry. So we have two questions, question number 6 and question number 7. For that, data has been given to us. So data says that steam condenses at 46 degrees Celsius in a surface condenser by releasing heat to the circulating water or cooling water. The water enters the condenser at 32 degrees Celsius and leaves the condenser at 41 degrees Celsius. So in that case, so here we have T saturated equals to 46 degrees Celsius. So for water, first temperature is 32 degrees Celsius, second temperature is 41 degrees Celsius. Now, you need to find that terminal temperature difference. So so here if you see, this is 46 degrees Celsius. Here it is 32 degrees Celsius. Here it is 41 degrees Celsius. This is your TW1. This is your TW2. And here is your T saturated. Okay. So this is your terminal temperature difference. So TTD is equal to T saturated minus TW2. So 46 minus 41 is equal to 5 degrees Celsius. Okay. So this is your question number 6. Now talking about question number 7. So find the logarithmic mean terminal temperature difference. So what is the formula for this? So this is your question number 7. So in short form, we can write it like this. So this is delta Ti minus delta T naught or Te divided by natural log of delta Ti by delta T naught. Now what is delta T initial? Delta T initial is T saturated minus TW1. So this is equal to 46 minus 32. This is 14 degrees Celsius. Then delta T, it's better to denote it by E. Five degrees Celsius. Then LMTD is 14 minus, sorry, 14 minus 5 divided by ln 14 by 5. So if you work this out, this will come out to be, please calculate. So I'm getting a value of 8.74 degrees Celsius. So if you are getting something else, please comment down, comment it down in the comment box. So this was question number 7. Okay, 8.74 degrees Celsius. Then next, so next is your lecture number 19. So from here we will start after taking a short break. So let's take a short break because almost 1 hour has passed since we have started this session. So we will take a short break and then we'll complete our remaining session. Okay. Okay. Thank you. Okay, so let's see the next lectures. Okay, so this is your lecture number 19. So in the starting of this lecture, condensate feed water system has been discussed, right? Right. Condensate feed water system where we discuss condenser, feed water heaters, cooling towers. Okay, so this has come from previous lecture only. Then next topic that has been introduced is regenerative cycle. So regenerative cycles we have discussed in modified Rankine cycle in that week where we have discussed the modified Rankine cycle. I believe it's the third week. Okay, so there we saw that how we can use some part of the steam that is expanding. So in midway, we take some part of the steam that is expanding and use this steam to heat our feed water. Okay, so this can be done in two ways. One is direct, then is second is first is your open feed water heater, second is your closed feed water heater. Okay, so this also we have seen there. So so this is your lecture number 19. Your feed water heaters. So so in your regenerative feed water heater, what is one is your closed feed water heater. So if you'll revise your content of week 3, you will definitely recall this. So something like this. Okay. So from 1 to, if you see, 7 towards 1 is your boiler. Okay. 1 towards 3 is your turbine. Okay. 3 towards 4 is your condenser. 4 towards 5 is your pump. 5 to 7 is your feed water heater. 5 to 6 is your feed water heater, right? Right. So, so this 5 to 6, this your feed water is moving, right? The enthalpy is increasing. This is because of the steam that we have taken from point 2 towards 8. Okay, so this steam, so energy, or yes, energy from this steam we are using to heat our feed water, correct? And closed feed water means this is a shell and tube type arrangement. Okay, then if you talk about open feed water heater, so its diagram is something like this. So in open feed water heater, what happens is your steam that you have taken from point 2, okay, in the midway when the steam was expanding, so this will directly mix with your feed water that is coming from your pump and is at 5. Okay, and this will eventually increase its enthalpy and uh, reach at point 0.6. Okay, so if you compare the two cases, one where the feed water heater is used and one where the feed water heater is not used, so you can see, so if you move from 7 to, let's say, 7 dash, okay, so if the feed water heater has been used, in that case only 7 to 7 dash distance this we have to cover, right? But if feed water heater has not been used, in that case we'll have to move our working fluid from a to 7 dash. That will more that means more energy will be required in that case, right? So in terms of energy, this gives us more efficiency, right? But it also comes at a cost, because in your turbine you are decreasing the work output, because you are taking some steam from your expanding steam you are taking from your turbine, right? That would have contributed to the work output of your vapor power system. Okay, but if you weigh these two, right, the gain and loss, so the gain is more in that case. That is why we opt for these type of changes in our whole system, right? So this is your open feed water heater. All right. Then your closed feed water heater has been discussed. Okay. So in terms of your heat analysis and pressure drop that your feed water heater sees, right? Because of flow friction also, right? So this has been discussed. And in your closed feed water heater, so zoning also has been done. So this is desuperheating, then is your condensing, then is your subcooling. So from the superheated state, when we want to move our working fluid from superheated state to saturated state, we use desuperheating. Then condensing is from your gaseous state to your liquid state. Subcooling is again reducing its uh, enthalpy, right? We want to again from saturated the saturated line, we want to move it towards left. Okay, so that is your subcooling. We again further we want to cool it down. So this is your subcooling, right? So these three zonings we can do in our closed feed water heaters, right? So but this is not a compulsion that we do such zoning. Okay, we can work with just two zones also, like superheating and condensing, or just one, where we have just condensing one, based on the situation that we have in our hand. Okay, or based on the design we have opted for. Okay, then next is your discussion on open feed water heater. So few points about open feed water heater that have been mentioned is that, so first of all, this is also direct contact type heater. Okay, then this is also called deaerating. Deaerating means removing non-condensables, okay, or non-condensable gases. For removing your non-condensables, right? So again, further discussions have been done on this open feed water heaters, but for this session, I believe this much is fine, right? And if we come across some questions, so we will see it there only. Then treatment. In boiler treatment, so if we want makeup water, right? So let's say we have lost some water that is needed for your boiler in your whole circulation, and we need to uh, make up for that water. So what do we need to do for that? So we have some uh, water supply from some other source. So for it to be of use for the boiler, what we need to do? So pre-treatment is required, which basically is your chlorine removal. Okay. Then is your demineralization. Demineralization, where we remove the ions or the minerals that are there in water, so that there are no reactions because of these ions in your boiler that can harm the boiler, right? Then evaporators also are used for makeup. Okay. So in evaporators, we get vapors. Okay. So we have a structure something like this, where we have here we have hot water, right? Some structure is like this. From here we give steam. Okay. This is condensed. Okay. From here, so this is your water, right? From here we get our vapors. So can also help this can also be used for your makeup, right? So all this comes in your boiler treatment. So your evaporators can be single effect, multiple effect, double effect, single effect, double effect, or more than this. Okay. So what happens in that? So vapor from here will act as inlet for another evaporator. So let's say one evaporator is this. So the exit of the outlet vapors of this evaporator will act as inlet for some other evaporator. So this series go on till we get the amount of vapors we need, right? The quantity we need. So this is your evaporators. I hope you have understood. So it is something like this. So from here, so this will be, so here we have steam, here we have outlet. So this this is evaporator 1, this is evaporator 2. Okay. So outlet of E1 is inlet of E2. Okay. So something like this. I hope you have understood, right? So this is outlet of E2. So this is about your evaporators. Then moving on to questions. Zoning in a closed feed water heater is not done by which of the following names? Superheating, subcooling, condensing, heating. This is done, this is also done, this is also done. But if you see heating is not any kind of zoning. That is done in your closed feed water heaters. So this is the correct option. So this was about zoning of closed water heaters. A closed feed water heater is also called as deaerating heater. So whether this is true or false. So deaeration is related to your open feed water heaters and not your closed feed water heaters. Correct? So this is a false statement. B. So I think this was it about your feed water heaters. But this you should remember, these two diagrams for your closed feed water heater and your open feed water heater. So these are important to visualize everything about your feed water heaters. Okay, then is your cooling towers. So this is a very lengthy lecture. Lot of topics. So first is your circulating water system. In your circulating water system, you have system classifications. So one is your once through system, then is your closed loop system, then is your combination system. So this circulating water system is for your, they are talking about your what, condensers. Okay. For your boiler, you have your feed water system. For your condenser, this is your circulating water system. Then classification has been done. Once through, so I hope once through, you by now you all well understand this term, right? Once through means it will pass once only. So we have seen it in other cases at different places. Okay. Closed, then closed loop system is there, then combination system is there. Then cooling lakes, spray canals, dry cooling tower. Then is your wet cooling tower. So wet cooling tower has been extensively discussed. So in it there are two major types. One is mechanical draught cooling tower. Then is your natural draught cooling tower. The main difference between mechanical and natural draught cooling towers is that in your mechanical you use some fan, forced draft fan or induced draft fan, to push your air through your cooling tower. Correct? In but in your natural draught cooling tower, we don't use any fan, neither a forced draft fan nor a induced draft fan. But here the movement of air is because of density differences. Okay, in the air that is outside the tower and the fluids that are inside the tower. So that leads to circulation. So inside the tower, the densities are lower and outside is higher. Okay, so that leads to air circulation inside the tower. Then psychrometric analysis, for that discussion has been done. So this is basically because here we have vapors, then air, saturated vapor, unsaturated vapor, all these terminologies we we come across while we discuss this wet cooling tower. So that is why we this has been discussed here. Okay. So lecture number 20, cooling towers. So this is circulating water heater. So what is circulating water heater? This supplies water to condensers. Circulating water system, sorry. So this supplies water to the condenser. Okay. Then next is your system classification. So in system, all these three will come. Okay. First is your once through. So once through is that type of circulating system where we take your cooling water from some natural body, okay, like pond, lake, or some other water body, and from there this water passes into condenser, right? It condenses the steam, gets heated up, and then again this is uh, released back to that same natural body from where it had been lifted. So this is once through. Okay, there is no closed loop. It is not like that the same water that has entered the condenser is exiting and then again entering the condenser. Okay, so this is once through. Okay, then is your closed loop. So what happens in your closed loop type of circulating water system? So if this is your condenser, this is your inlet, this is your inlet, this is your outlet. So what happens here is you have a cooling tower. Okay, you have some cooling tower. So it will go in this cooling tower. Okay, then again it will come back. Right, so this is your closed loop. This is your condenser. This is your cooling tower. But also, let's say you have a water body here. Let's say this is a water body. So in this loop, if there is somehow leakage or loss of water, in that case for makeup, we use this. Okay, so this is your closed loop, right? Then third is your combination system. So what happens in your combination system? We use both once through type of arrangement, and then we also use your cooling tower. Okay, but what happens is that it majorly remains a once through type, and we release the water that comes from the outlet of condenser in the water body only. But before releasing it to the water body, we cool it down, okay, by means of cooling tower. So this is your combination system. Okay, combinations type of system used for circulating water, right? Okay then. So this is about your system classification. Then is your cooling lakes, right? And your spray canals. So spray canal, in your spray canal, your heat transfer basically is because of evaporation, conduction to air, and partial radiation. So these two also are related to your circulating water system. Okay, all right. So these basically receive your hot circulating water that exits the condenser. Okay, so from that context, these have been discussed. Then is your dry cooling water. So what is the difference between dry cooling water and wet cooling water? So dry cooling tower and what wet cooling tower. So in your dry cooling tower, your heat transfer in terms of sensible heat only. Okay. And in your wet cooling tower, this is sensible heat. I hope you know difference between sensible heat and latent heat, right? Latent is hidden, right? Where no phase changes are taking place. Sensible is that where phase change is not taking place. Okay. So sensible heat then is evaporation. Evaporation also leads to cooling of the circulating water, right? So this is how you differentiate. This is the point at which these two cooling towers differ, right? So for the whole structure of these, the dry cooling tower, you can refer to the lecture number 20. So I'll give the link in the description. So from there you can see, right? So about wet cooling tower, if you see, so what happens here is, so you have this tower, okay? So you have tower here. So from here, you get air inside, okay? And somewhere here you have your fill, okay? Where you have uh, your water, circulating water from your condenser outlet, okay? That enters here. Then by virtue of this movement of air from outside, the evaporation takes place, okay? And also there is heat exchange with the air, right? That we call sensible heat. Then evaporation also there. So this basically leads to cooling of your circulating water, okay? Then this movement of air can be done by two ways. One is your, so this comes in then circulation. Sorry, sir, not circulation, but classification. One is your mechanical, one is your natural. So if your fan is here, this is ID. If your fan is here, this is FD, forced draft. This is induced draft. Okay. And if there are no fans, and based on density difference, density of air atmosphere, this is density inside. So density inside will be less than density atmosphere. Okay, so this will lead to air passage, and this comes in your natural draught tower. Yes, all right. Natural draught type, your wet cooling tower. Okay, so this is it about your wet cooling tower. And in your psychrometry, you talk about humidity, because humidity comes into picture in wet cooling tower. So when air enters, it is not fully saturated. Okay. So by saturation, I mean the vapor content in the air. So there is a limit to which air can hold vapors. Okay. So that is its limit, and when this limit reaches, we called the air is saturated. It no longer can take vapors. Okay. So when air enters, it is unsaturated, right? So evaporation in the tower takes place, and this becomes saturated. Okay. So all the thermodynamic analysis related to this saturated, unsaturated state, for that this humidity has been defined, right? So different definitions are there. So one is your relative humidity. So what is your relative humidity? This basically is the partial pressure of water vapor in air to the partial pressure. I'll write partial pressure as PP of water vapor WV when air is saturated at same temperature. So we have some temperature at which we have some air that is not saturated, that is unsaturated. For in that unsaturated air, the partial pressure of vapor. Okay, so vapor will have some pressure, air will have some pressure. So the partial pressure of that vapor, when we take its ratio with the partial pressure of air in its saturated state at the same temperature, that is your relative humidity. Okay, so this is a term to define the humidity. Then is your absolute or specific humidity. So what is this? So this is basically the ratio of mass of water vapors in the air. So we have some air, either saturated, unsaturated. Okay. So if we take the ratio of the mass of water vapor in that air to the air itself. Okay, air without vapors. Okay, that is dry air. In that case, what we get is specific humidity or absolute humidity. Then there is one more definition, that is degree of saturation. So what is your degree of saturation? So this is ratio of actual specific humidity to the saturated specific humidity. Okay. So this means that if we have some air, let's say it is not saturated, in that case, at some temperature it is not saturated. In that case, it will have some specific humidity, that is mass of vapor to mass of dry air, right? Then if this air becomes saturated at the same temperature, in that case it will have again some specific humidity, that is the water vapor content in it. So this specific humidity and the specific humidity of unsaturated air. So we divide the unsaturated with the saturated, and from here we get the degree of saturation. So the degree or the extent to which your air is saturated, this is the measure of that. Okay, so this is degree of saturation, right? Okay, then there is wet bulb temperature and dry bulb temperature. So if you measure the temperature of air using a thermometer, right, that is your dry bulb temperature. But in case your bulb of the thermometer, right, bulb that takes the heat, right, to give us the temperature value, right? So if mercury is there, the bulb will take the heat and the mercury will expand because of heat. Yes. So the bulb is taking that heat. So if we make our bulb wet, right, in that case what will happen is the outside temperature will make this wet bulb, right, or the water on the bulb evaporate, right, and this evaporation will cause cooling, right, and the temperature we receive on the thermometer, it will be less than the dry bulb temperature, because we know evaporation causes cooling, right? But then one more thing is there, this wet bulb temperature depends on the saturation of your air also. Okay, if the saturation or the vapor content of the air, if the vapor content is high, in that case the evaporation from this bulb will be slow, right? And if the vapor content in the air is very less, in that case this evaporation will be high, right? If you compare these two cases, the latter case, for the latter case, the wet bulb temperature will be lesser, right? Because more evaporation takes place here, right? Which has caused more cooling and thus more less temperature. more reduction in the temperature when compared with dry bulb temperature. Okay, so this is your wet bulb temperature and your dry bulb temperature. So this is it about your lecture number 20. So in the psychrometric analysis, numerical expressions are there, right? So for that you can refer to lecture number 20. You'll find it in the description. Then moving on to questions. So about circulating water systems, here question has been asked. So this is once through, heat is discharged back to the source. Heat is discharged back to the condenser. Heat is discharged back to the source. So if you see once through the heated water is discharged to the source. That is correct. It is not given to the condenser. So this is not right. Second one is not right. And if you see the third statement, it is in closed system it is discharged to the source. No, it is given back to the condenser. In that case, second and third statements also are wrong. So if you see your A, B, C, and D options, it comes out that A option is correct. Okay. So this was your question number 10. Then so in your cooling tower, wet cooling tower, you define range. Okay, one parameter range. So this is basically a difference in temperatures, in difference in two temperatures. But what these two temperatures are, so this you have to answer. So range basically is the, for a cooling tower, it says so wet bulb temperature has been mentioned, exit temperature of cooling water. Okay, then incoming warm temperature has been discussed. So these three, on based on these three temperatures, options have been written here. So range, if you see the definition of range, this basically is the difference of incoming warm water and the exiting cool water temperature. Okay, so option C is the option that we are looking for. So the temperature at, just give me a second. So yes, so range is the difference in the incoming warm water and the water incoming warm water temperature and the exiting cool water temperature. Okay, so this is your range, C option. Then 12th question is, which of the following is true about dry cooling water? So four options are there. Heat rejection. First is heat rejection from the circulating water is in the form of sensible heat only. So this is correct. Then initial temperature difference parameter is important here. So that is also correct. Initial ITD, that is initial temperature difference, basically is temperature of fluid entering tower minus temperature of outside air. Okay, so no evaporation. So evaporation is not of concern here in dry cooling tower. Only sensible heat. Okay, so if you see the options, C option is correct. Both 1 and 2 are correct. Okay, then next question. So this is about mechanical draught cooling tower. So if the flow in the fill, so if you see the tower here, here the tower is. So if it says that if the flow is in this direction, right? In that case, and your air is in this vertical direction, right? In that case, it is it is what type of tower? Okay. So this is cross flow type. Okay. If the flow of this in the fill had been in vertical direction, this had would have been counter flow, right? The air and the this water would have been in opposite direction. Hot water would have been in counter flow directions, right? So this is in that case cross flow type tower. Okay, so this is your question number 13. Then is your question number 14. So this talks about relative humidity is the ratio of what is relative humidity. We have seen what is relative humidity is the ratio of mass of water vapors in air to the mass of dry air. So whether this is correct, this is not correct. This is the definition of absolute humidity. Relative humidity is when we uh, compare the partial pressures of water vapors in unsaturated and saturated states, right? So in that case, this is a false statement. So B option is correct. Question number 14. Question number 15. Dry and wet bulb temperatures are same for saturated air. True or false? So when the air is saturated, there will be no evaporation from the wet bulb. Okay. In that case, no cooling, extra cooling. In that case, temperature will be same. So this is true. So dry and wet bulb temperatures are same for saturated air. Okay. This was question number 15. Then last question of the session, which says that wet bulb temperature is always less than or equal to dry bulb temperature. So this is also a true statement. Okay. This is also a true statement. We have seen in our discussion that wet bulb temperature is less than our dry bulb temperature because of evaporation. There is cooling effect is sensed by the thermometer, and this cooling effect depends on the saturation of air also. So higher the saturation, less will be this cooling effect, and lesser the vapor content in the air, more will be this cooling effect. Okay, so this is a true statement. In that case, we are done with our today's session. So I'll conclude today's session. There were three lectures. First lecture was on your condensers, okay, steam condensers. Second lecture was on your uh, feed water heaters. Third was on your cooling towers, right? In your surface, in your condensers, in your steam condensers, we majorly focused on surface condensers, right? And we also saw direct type of condensers, right? Then in your next lecture, you saw feed water heaters. So there is open feed water heater, there is closed feed water heater, right? So these two cases we discussed. And third was your cooling towers, right? So circulating system, water circulating system that is used for condensers, that was discussed, right? And then there we saw classifications of such circulation systems. Then we discussed the cooling towers, where we majorly focused on wet cooling towers. So there are two types. One is mechanical draught cooling tower. Then is second is natural draught cooling towers. And what are the differences we discussed. And we discussed questions also based on the content, and two numericals we discussed, right? Based on the condenser only. So this way we have conducted today's session. I hope this session was informative and of help, and will be of help to us. Thank you for watching this session. And next session again will be on next Tuesday at the same timing, 6 to 8 p.m. Till then, bye.